We must now learn what is meant by series and parallel resistors and how they can be dealt with. We saw this simple circuit before with its single resistor. Now suppose that instead of this one resistor, we have two resistors connected end to end. We would show them like this on a circuit diagram, and we would say that R1 and R2 were connected in series. Any number of resistances can be connected in series, and so can cells or any other circuit component. Suppose these three resistors are 3 ohms, 8 ohms, and 24 ohms. What do you think RT, the total resistance, would be? Most people would say 35 ohms. That's 3 plus 8 plus 24, 35 ohms, and they'd be right. To get the combined resistance of resistors connected in series, you simply add the individual values together. So R1 plus R2 plus R3 equals RT equals 35 ohms. This combined resistance can now be used with Ohm's law to calculate the current in the circuit. 70 divided by 35 equals 2 amps. And this same current of 2 amps flows through each of the resistances. So with series resistances RT equals R1 plus R2 plus R3 and so on. But there's another way of connecting electrical components. It's like this. When the resistors are connected side by side, they are said to be connected in parallel. When connected to a source of power of, say, 20 volts, there will be the same EMF of 20 volts pushing current through each resistance. But it will not be the same current in each of the 3 paths. Where the resistance is lowest, say R1, the current flowing, I1, will be greatest. Where the resistance is greatest, say R3, the least current will flow. The total current flowing, IT, is equal to I1 plus I2 plus I3. Now we know that the greater the cross-sectional area, the lower the resistance. Connecting resistors in parallel is like increasing the cross-sectional area available. There is, as it were, more room for the electrons to get through. So the equivalent resistance RT of 2 resistors in parallel is less than either one alone. And in fact, to calculate RT, we can't just add resistances together as we did with a series circuit. We have to use a formula. The formula is 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. Now suppose the resistors are 3, 8, and 24 ohms, as we had before in the series circuit. Then 1 over RT equals 1 over 3 plus 1 over 8 plus 1 over 24. Simple arithmetic now shows us that 1 over RT is equal to 1 over 2. So by inverting RT in the parallel case equals 2 ohms. You can calculate RT in this way for any number of resistances in parallel. For 5 resistances, say, the formula would be 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 plus 1 over R5, and so on. Sometimes circuits are connected partly in series and partly in parallel like this. They are called series parallel or compound circuits and are quite easy to deal with. Take this one. To find RT, we find first the equivalent resistance for the parallel part. That is 1 over 3 plus 1 over 6, which simplifies to 1 over 2. So the resistance of this part of the circuit is 1 over 2 ohms, which we must now remember to invert to 2 ohms. Now we can think of the circuit as a simple series circuit, with 4 ohms and a 2 ohms resistance. So RT equals 6 ohms. Let's look at one more. This time we must deal with the series part first. 1 plus 3 is 4. So the upper branch is equivalent to a single resistance of 4 ohms. Now we can apply the formula to both branches. 1 over RT equals 1 over 4 plus 1 over 12. That equals 3 plus 1 over 12, or 4 over 12, which is 1/3. So RT is 3 ohms. There's one more circuit we want to deal with. In all circuits we've done so far, we've ignored the resistance of the wires connecting the various components of the circuit. This is often quite in order. However, sometimes long cables may be involved, and these may have considerable resistance, causing a voltage drop across them, which has to be taken into account. For example, if a cable is 20 meters long and has a resistance of 1 ohm per meter, then the resistance of the cable will be as much as 20 ohms each way. If a 5 amp current is flowing, we could use the Ohm's law triangle to show that there is a voltage drop of 100 volts in each cable, a total of 200 volts. Suppose we have a circuit where the resistance of each cable is known to be 0.2 of an ohm, and the battery is providing 200 volts to drive a current through a load of 99 6/10 ohms. Can we calculate the voltage drop across the load? Well, the total resistance of the circuit is 99 6/10 plus 0.2 plus 0.2. That is 100 ohms. So what current is flowing? V over RT gives us that, and it is 2 amps. The voltage drop in each cable is given by I times R. That is 2 times 0.2, 0.4 of a volt. So the total voltage drop in both cables together is 0.8 of a volt, which makes the drop across the load 199 2/10 volts. So we can deal with the resistance of the cables if we need to. During this part, we've learned how to calculate the equivalent resistance for resistors connected in series, when RT equals R1 plus R2 plus R3 and so on. We have learned how to calculate the equivalent resistance of resistors in parallel. 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3 and so on. And finally, we heard about the resistance of cables. The next part will be about electric power.